Well, good afternoon, everybody. I'd like to thank you all for staying here through the end of the flight software workshop. I'm going to try and go pretty quickly here. My name's John Lucas. For those of you who don't know me, I work at NASA IV&V in Fairmont, West Virginia. We do independent verification and validation on flight software. So a little overview of this presentation. I'm going to talk quickly about the team I work for at IV&V, a little bit about the NASA operational simulator for small satellites and the miss it and driving it, and then we'll go deeper into all the components and talk about the demonstration we're working on as well as improvements and a quick roadmap. So a little bit about NASA IV&V. You guys know that we do a lot of static code analysis. We work on a lot of big Class A missions, but the team I actually work on is a very small subset of NASA IV&V as a whole. We're called the JSTOR or ITC team, stands for Independent Test Capability. And so what we typically do is we take unmodified flight software binaries, throw it in a simulator such as Simix, and we're able to pause, fast forward, replay time to simulate missions and different kinds of testing that you can't normally do with flight hardware. And so this allows us to do an independent and dynamic tests so that we can check for those things such as the one light that breaks the entire system or a stuck thruster test that you really can't emulate on hardware, right? Because you don't want to break your entire mission. Two of the big ones we have going right now are the SLS simulator, or S3, or the James Webb Space Telescope sim called JST. A little bit about our Cubesat mission. That's why we're here. This simulation of Flight 1 is essentially going to be the first Cubesat from West Virginia. It won the Cubesat Launch Initiative Challenge and will be flight ready for April 2017. So right now we are really kind of starting environmental testing and getting ready to go into Vibe here in the next couple months. And so it's driving a lot of our NOS3 development, right? So we have two different teams that are working on this. We've got West Virginia University that we're partnered with. They're delivering most, if not all, of our payloads. And then the ITC team that I work for is essentially in charge of everything else. We're working on the flight software, we're doing all of the integration, and then we're developing simulators so that the rest of the flight software team as well as the payload team can test their software and test basically their components without as much hardware. So a little bit about NOS3. There's a whole bunch of uses. Essentially, so far we've used it for a lot of early flight software development. We've been able to really shift the flight software development forward in our schedule. Even though we're just about now done integration, we're almost done flight software development as a whole, which is kind of amazing. I didn't think we'd get that far. We've used it for mission planning, actually doing practice orbits and mission operations training for how we expect to basically communicate with the satellite on the ground, as well as doing verification and validation, which we do every day. So the really great thing about NOS3, or this simulation environment I'm going to continue to talk about, is that you can take basically an entire flat sat, like you see in the top right picture there, and combine it and run it on a laptop, right? And so that's really what our team does. We work on bringing these giant big systems that are extremely expensive or immobile, right? Really time-sensitive systems down onto running on a virtual machine on your laptop. So we simulate each thing down to the component and usually register level. We've got a cadet UHF radio right now, different sets of batteries and EPS, some generic science instruments that we're planning on flying, as well as the sensors on the processor itself, antenna, and GPS. So a little bit about the components we're utilizing for NOS3. We're using 42 right now, which is a Goddard Space Flight Center product. You can think of that as very similar to SDK. We're running CFS, Cosmos, and then to basically solidify our development environment, we're using a Vagrant VirtualBox and virtual machines, right? So every developer can essentially run this script, bring up the exact same development environment, and there's no issues between people, well, my host is better than your host, or any issues like that. So those are all the open source tools that we're using. In addition to that, we've also added a hardware abstraction layer, our own simulators we've developed, and then the middleware. So the NOS engine middleware is essentially able to drive time throughout the simulation, as well as communicate and simulate your bus on the spacecraft. And I'll show that a little bit more later on. So the general architecture of NOS3. Well, the big outside box there that you can think of as your host computer running whatever OS you plan to. As long as you can install VirtualBox and Vagrant right now, you're good to go and you can run NOS3. The only thing really shared inside are your synced folders. So you'd be able to, if you wanted to develop outside of your virtual machine or CM outside of your VM, you can certainly do that, or you could do it inside and keep everything contained. Inside your virtual machine, you've got your ground station. Right now we're running Cosmos. You've got our flight software, CFS, all of the middleware or glue, which is that NOS standalone server or NOS engine as I called it. Then we have all of your simulators running. Now you can run all of your simulators, one of your simulators, doesn't really matter, whatever you're trying to test at that time. Right next to that you actually have your dynamics provider, your environment 42. And the nice thing about this whole setup is if you really choose to work with SDK, we can find a way to drive SDK and you can sub one of these parts out. Or for example, Trick. I know a lot of people prefer those. Or if you have a different ground station, for example, too. So a little bit about the hardware model. You could kind of see it in the last diagram, but it didn't fully come together. Your flight software is basically sending messages or any kind of communication protocol through your NOS engine interface, right? So your NOS engine interface is essentially stubbing out things like I2C, SPI, UART, Ethernet even, and talking directly to a hardware model where that's managing your registers, your state machine on the hardware and things like that. And your hardware model is essentially getting fed and providing data back to your environmental data provider, which is 42 in this case. So a little bit about the build system. We're using CFE 6.5, the newest one that's released open source. Currently we have CMake basically baked into everything. And our goal here, just like our other simulators, is basically test as you fly, fly as you test, the old NASA motto and mantra. So what we essentially do is we're stubbing out your GOM space drivers, which is our actual flight computer, and running basically stubs to NOS engine. So you're running the full flight code. You're actually able to run your all of your hardware libraries as well to test your hardware. The only thing that's changing is your actual driver level, where we're switching out basically GOM space drivers that are provided for our NOS engine calls. You're even using the same headers, so literally none of your flight hardware from basically that first orange box and above needs to change depending on if you're running flight or if you're running a simulation setup. I'd also like to point out in this diagram, although it's kind of small, we've got in the middle there, that first tree is simulated hardware. So that's if you're running everything in a full simulated environment. You also have the option on the right side, the very bottom right, to run basically hardware in the loop, right? So if you have a single piece of hardware, you're able to plug in that hardware, actually communicate with it, and utilize simulated components at the same time for the remainder of your hardware. So here's just a quick example of hardware in the loop. A few of the different things we've utilized is basically a Raspberry Pi 2. You can see that's basically a snippet of your desktop. You can run this whole simulation on a Raspberry Pi 2, and then if you're ready or when you're ready, you can plug in a camera, for example, like I have there, and be able to actually take a picture, and you can see that there on the screen. We also have a few different other options. You can use an aardvark, Bus Pirate, open source tool, or an FTDI cable basically for UART. Here's a quick demonstration. All right, so this is essentially your VM environment. You can see there we've got a NOS Cube logo on the left. Currently we're able in our host environment to compile for both NOS Cubed and AVR. In the open source version, you're only allowed to compile for NOS Cube due to some ITAR restrictions, but we're working on that. So you can see I built this flight software using that NOS Cube button, and then I was able to easily run it. You see the flight software and all of our components popped up. We've got 42 running your environmental data provider there on the left. Basically able to move around and actually see space and see where your spacecraft is. There's NOS engine, that's your middleware once again. You can see it actually popped up and showed my science I2C bus as well as my system I2C bus and the UART connections that I have to the GPS. Here's Cosmos running in the loop. And you can see that once I actually connect Cosmos, I'll start to get data through TO Lab right now is how it's set up. And then there's flight software, and I'm able to command flight software here from Cosmos. And so right now in this current configuration, you can think of this as basically connected direct from your ground station to your flight software. There's no delays, there's no throttling or anything like that. That is fully capable, and we actually have that already for our ITAR system using the cadet radio. But we are currently working on a generic store and forward radio for open source use. And so you can see I can send a command from the ground station up to the spacecraft, and it's received, and then I'll get telemetry back from it here in a second. And so right there, here in a second, is telemetry coming back down from the spacecraft. And so this has been extremely useful for us as not only debugging, but setting up our ground station in general. So moving on, we've got a lot of planned improvements for NOS Cubed. Unfortunately, as our simulation of flight mission is actually coming to a close, it's driving a lot of our NOS Cube development. A lot of our focus and our team is essentially working on both of these products at the exact same time. And so we're really focused right now on getting STF1 finalized and tested and environmentally checked out and ready to sit on the shelf until it finally launches on the Rocket Lab's Electron rocket. But some improvements that we definitely have had already from the environment from presenting at SmallSat are basically a GUI environment, being able to change your OS. Essentially, a lot of people don't want to use the new Ubuntu. Some people prefer Mint, other things like that. So we'd like to be able to change that. We'd also like to change the number of VM providers. We use VirtualBox. Some people prefer VMware. And so we'd like to make all of these things configurable, right? And add a little bit more protocol support, things like that. If you can think of anything else, please let us know, and we'll be glad to add it to our list and essentially add it to our roadmap here. So NOS Cubed 1201, that was our most recent release. It actually released this week. It hasn't even officially gone out to the public yet. It will here as soon as I get back home and can send out the emails though. We've added all those hardware in the loop capabilities I've shown there, upgraded the version of NOS Engine, able to run on the new Ubuntu version, 64-bit, so that you don't have to worry about 32-bit dependency problems and things like that. And then we've got a little bit more plans here spec'd out in the long run as far as adding that GUI, running faster than real time, being able to control time, things of that nature. All right, well, I'll just open it up now to any questions. I'd really like to keep this informal and get a lot of feedback from you guys as this is a workshop.
Yeah, thanks.
Yes, sir.
I would like to ask about the possibility to inject failures during the simulation runs, so you could test, let's say, diagnostics engines and stuff like that.
That's it, exactly. We developed actually NOS Engine initially as a middleware for our big missions, so we can inject faults into the links as they pass between two objects. You can completely cut lines. You can log all traffic across a specific channel and things of that nature, so that's very possible. We just haven't exactly gotten to that point yet for our mission. And so as soon as we do, we'll document that as well and include that with the rest of the documentation here. But it's definitely possible right now.
Okay, thanks.
Dave in the back.
Yep.
It's more a comment and just an outline so everybody can hear it, because I think we all have many variants of the Cosmos database for CFS.
Absolutely.
And we should really either make a public project or do something where we're all kind of coming from the same.
Yes, we do need, we have that GitLab repository, but that's only open to NASA. I'll see if I can open one up, at least for CFS and us that are already on that GitLab, and see if we can combine them all and make sure that we're...
Combine them or make and get a public one going. Maybe, or maybe even Ball could host it. We could talk to them. But I'm just kind of throwing it. I know there's talked to probably 3 or 4 people. We all got our own flavor. So, and I don't know if you've made, I guess there's another, sorry. In terms of Indianness in the Ball database is a little too technical maybe, but we should probably figure that out, because right now it's hard-coded, I think, the Indianness in the database.
It is, yeah.
But
We've actually had a lot of problems in STF1 by itself. We're running the new GomeSpace A3200 NanoMind, and that's even different than Dellinger in that OS packed no longer works for the free RTOS that we're running. And so that's caused a lot of issues with packing all of our telemetry, unpacking things as they come from the ground, and so we've seen a lot of problems with that so far. But that's definitely something we need to look into for Cosmos.
Okay. Sounds like a discussion on the webpage. So
absolutely.
Yeah, I guess it's ultimately, in the near term, they're actually going to be derived from the EDS, so that will be auto-generated with the CMake. So
yes,
mid-summer, we'll have a real solution to this that's embedded in the toolchain.
Fantastic.
All right.
Any more questions? Any kind of improvements? You just want to yell out and I can echo it?
No, there's probably still somebody in Australia listening.
No problem. What are we, like 30 seconds behind?
You have a question?
Could you just, what is your store and forward radio that you mentioned in passing?
We're utilizing what was the L3 Cadet UHF radio. It has now been taken over by SDL, the Software Dynamics Laboratory. They are soon to make another batch of them, I believe, but it is UHF band, basically for Wallops. And so us and a few other Goddard Space Flight Center missions are flying the same radio in order to communicate with Wallops.
Store and forward means what protocol?
Store and forward is essentially, it's got 4 gigabytes, I think, of storage on the radio, and so we're basically pushing data to it until it finally gets a ping from Wallops, and then it will shoot it all down at once at 5 megabits per second. We're also looking at a lot of different other hardware configurations. So if you're building a small sat, please send me the specifications of your hardware so that we can build simulators that actually fit the community and what you guys are using. Yes?
Yeah, for the simulator side, could you talk about like what it can do relative to real time? Because typically Symix runs a bit slower than real time, and CFS usually runs at real time. Like, how do you guys cope with that?
So essentially, we're driving time throughout the entire system. And so right now we don't even have, as for our mission, we do not essentially drive an external environmental data provider yet. Our mission does not require that currently, and so that's our next step. Essentially, we're going to work on simulating like a Blue Canyon device for attitude control and determination. But right now, as far as that time sync, it's really been an issue between the simulator and everything else. Usually we pretty much just wait for everything to finish and then we can increment the next time step. So it's not really a Symix-like environment here, but that is our bread and butter and basically where we come from as far as Class A missions. But for open source, since that's so expensive, we can't.
Class A missions, you drive time through the system?
Through Symix, yes. Any more questions?
All right, thank you.
Well,
John.
thank you all very much.